Hello. Hello, I am Alberto Redondas, and we are talking about the aerosol depth in the Euronet. This aerosol European Brewer network. It was the acronym for a cost action. And we talk first about the Euronet, and then specifically about the EOD in Euronet, our new measurements in Euronet, and finally the VCC calibration, what we use also calibration to calibrate also for EOD. So Euronet was a cost action. It was to try a specially consistent network of Brewer spectrophotometers. This is a spectrometer providing ozone, SO2, UV, and EOD. It was a cost project from 2013 and 2017. As you see, most of the instrument was collocated in Europe, but now it's extended to other parts of the world. And now we have 70 spectrometers and around 61 stations. The main characteristic for Euronet is everything is central processing from raw data, and this allows us to have the traceability of the measurement. So we are considered a user reference network for also mainly for ESA, air quality in Copernicus, and some Copernicus climatic studies. At the beginning, before the cost action, we have in Europe this Brewer spectrometer is mainly used for ozone, and we have 50 stations independently calibrated, independently processing data, independently managed. And its own station process and submit his data to ozone database, that is WDC in Canada, and then Canada. Another issue we have is that we have calibration provided by private companies. We use the experience we have in Spain. We make a small network for Spain, for Spanish and Portuguese spectrometers. Also, we have the Brewer Calibration Center, and we use all this experience to set up the Euronet. Basically, from the station, they send level 0 data to the database. At the same time, we store all the calibration and characterization of the instrument, and we produce what we call level 1 data, level 0 data. The level 1 data is just for storage, and it's only accessible by the operator. And we make a copy of the raw data to WDC database in Canada. WDC database also store, we also store raw data from this database. Then we process the data, and we have two levels, one real time. In the real time, we have two levels, one because the data is changed during 1 week, and we call 1.5. The 1.6 is the data, real time data will not change. And we have finally the level 2 data, when we have 2 points of calibration that you can trace the calibration. Then the data is sent to the standard database for ozone, UV. In the case of the UV, it's not sent to any database, but ozone and UV is sent to WDC, to NDAN, to EBDC. It's an open project. We have all the documentation and also the code for the process open and free available in the Bitbucket repository. It's documented, all the procedure, and we try to have this one testable. We are very happy. We were evaluated with this Gaia Clean project to evaluate the different databases in Europe, and we are very happy. Our score, mainly in the documentation and statistic characterization, we have almost the maximum score, so they think that our data has traceability and this has compatibility. The only lowest score we have is in the security and the user feedback mechanism, but I think that ozone data doesn't need to be too secure. Also, the Euronet was recently become an associated network for NDAC. And not only we send the data to WDC, so from WDC you can search the Euronet data. And finally, something important for the participants of the network is that your data is properly acknowledged. So we have a DOI for the data produced in the Euronet. So with the data and metadata we have in the database, we can generate and all data needed for the landing page. We will have a DOI for each product and for each station. So it will be one DOI for ozone, one DOI for UV, and one DOI for UV, and for every station. What will change is when you update the data, there is new data, you don't have new DOI, just is we assign it as a collection, so every product at every station will have this DOI. Now it's in the final testing, and I show you the landing page that is follow this ABDC and ESA format. One of the things that the Euronet is always from the beginning try to, what we call in WMO terms capacity building, is to share our experience. So we organize regular course for training for the operators. During the cross-section was every year, and after the cross-section finished, we try to have a continuous course. During the pandemic was online, and probably the next one will be in Brazil next January. And it's something also important for Euronet, how we support, I don't know if you know what these AC countries is, developing countries as considered by the Vienna Convention. So it's one of the objectives to help to developing countries to produce the data for Vienna Convention. So in a part of the operator course, we have important to have regular calibration. The calibration is stored in Euronet, and the software for Euronet can be installed in every computer or run remotely. So our setup will give high submission rate. Now we have the experience with South America. This is for our common language for Spain, but it's really an improvement for developing countries who have to restart their ozone observations. This is just some start that how the network evolved, and we don't feel too much the pandemic, and we have now 61 this year Brewer sending data in real time, and it's around 8,000 observations per year. And we have for queries, you can access the data whatever in two ways. One is to download the files, and the other is to query the database. And here you have the proportion that the file download and direct query to the database. It is what we have developing now. Now we have include the uncertainty determination in Euronet. We have a new product for UV. Now we have what we call level 1.6 that includes the SIG algorithm who correct UV spectra for wavelength shift. And finally, we have the level 2, we also include the cosine correction. And what is more important for this meeting, all the AOD specific measurements and tools also related to AOD. But it was the next part of my talk. During this cost action, we developed this system to have aerosol optical depth for all the European network. Most of the work that we follow is made by Javier Lopez Solano, who worked with us. And basically, we apply the equation you already know for ultraviolet wavelengths that use the Brewer to measure ozone. The particular of the Brewer, it has two modes of operation and has very good wavelength resolution. In one mode of the operation of the Brewer that is used for measure ozone, the measures are relative, we don't move in the grating, and we have 6 quasi-simultaneous measurements. Instead, in the UV mode, we have moved the grating and scan all the wavelengths. In the AOD mode, we try to combine the both methods, so we move the grating to certain positions, but use the slit used for the ozone. So we can have around 30 wavelengths, much faster if we scanning in this wavelength. We can use most of the ozone calibration for the AOD calibration. There are some exceptions. For example, for the instrumental part, we have to characterize the polarization. And, but for the ETC transfer, what is using for ozone, we can use practically the same to the UV. For the reference instrument, we make the Langley calibration, and using the campaign, we transfer to the network instrument for the reference instrument. This is an example. For ozone, we have filter correct. Everything is, they are not absolute measurement, they are relative measurements, and we use the log space. Where in aerosol optical depth, we don't use the log space, we call the real space, and we use every particular wavelength. We extend the measurement for the ozone, the wavelength ozone, to include this new measurement, what we call GG measurement. And this is an example. At the left, you have the street characterization for the Brewer that we make in that month. And then when you extend the wavelengths, you can go from 310 to 360 and derive the OD in this particular wavelength. Every color, these are different position of the gating. We use all the experience we have. This was during the month project that we characterized the reference instrument to transfer the calibration for the OD. In this case, this is the OD mode, and you can see all the slit we can measure in the UV spectrum. We have included in the Euronet the calibration. It's just a CCS file with the, basically attenuation of the filter, ozone cross-section, and filter attenuation. By right now, we make a lot of approximation, mainly for the temperature that we have to take for relative measurements, but we are developing new tools to provide the calibration also for ozone and for IOD, and now the Langley tool can be accessible for everyone. You can have more information for the calibration data. It's our wiki page. Everything I said before is we try to document all the processes of the network. This is for the data. This is for the configuration. This is more or less what you get from the web. For all the data, you just put the brewer, the date, and you have the IOD for all the wavelengths that it's measuring. And this is for most standard for the GA measurement. I go fast. This is an example how we transfer the calibration for the 185, that is a full calibrated lasagna, and we transfer the calibration to the campaigns. This is, as you see, the three instruments that we have at lasagna. And then this is the results, what we can have. So for some of the instruments, the agreement is pretty good, but for others, it's not so good. Mainly, we're investigating for that. Most of the results are discussed in this paper, and we have now 4 calibration campaigns that we perform this AOD calibration. This is an example for 2017 with different brewers, and as you see, and also in this one, you can see the variability between the brewer during the campaign. In the 90 campaign, we realized that we have quite good agreement, mostly for double brewers, so double spectrometer brewer, but the agreement with single brewer was not very high. We are thinking about stylight or the polarization will be different in the single brewer because the grating is also different. This is also some example. So we are also working to try to track the changes. So in this example, we apply the whole calibration during the campaign, and we try to see if the instrument change as they change in the ozone calibration. This is preliminary results for this standard range comparison. For one wavelength, this comparison with the Aeronet, it works pretty good, but for some of them, the comparison is not. We don't know exactly if we are missing some absorbers, or really, I don't understand why in some wavelengths with the same methodology works pretty well and the other is But this, you see, it's a work in progress for the new measurements. And this is just a last example for the forest fire at Isanya that we see. You don't see here anything, but it was our filter of measurements. Then when you remove the filter, you see the highest value that we derive in the fire. And I think that is all. Just to talk about the calibration for FBCC that we use for calibrate ozone. The next calibration will be in Brazil in January, and this is, I want to show you just the activity that we have for calibration. At this time, we only, the FBCC is the only way that you have to calibrate the OD for the brewer. And that's all. Thank you.
Thank you. So do we have a question from the audience? Yes. Mike is coming beside you.
Thank you. Thank you, Alberto. Very interesting with IOD with the brewers. Do you use the same algorithm then as the algorithm used by International Ozone Service, or it is something different?
I don't think we use the same algorithm because I don't know if it's published, the algorithm of International Ozone Service.
Because, for example, our station, Lindenberg, they do the calibrations of the brewers.
Mm-hmm.
And for some brewers, Martin Stanek made an algorithm, and it ran an IOD retrieval algorithm. And I think this is based on what Borovia presented something like 3 years ago. It's not the same. So you have separate methods. And
the problem for me to answer this question is I know that Bologna provides this COD, but I never it's not documented in some way. I cannot say that this is the same. So our algorithm is in the paper. So basically, because I think they don't use the polarization calibration, this was the main difficulty we have in Evronet to take into account the window. But because the other is not published, I cannot say that this
okay,
is
so it's not a common project in a commons. And about your Langley, very technical question about you told us about a Langley routine. Is it a GBDW basic routine to run the brewer and so that it makes Langley plots, or is it only a retrieval algorithm?
It's a retrieval algorithm. So
okay. So you do around the day direction measurements, and then you apply Langley. But you need to have to be at the site, Langley friendly site. So you cannot do it in the middle of a.
You can be anywhere.
You can try.
The results will be not valid if you are not a very stable place. So it has to be Manualoa, Isanya, or clean or stable environment.
Sure.
And you can use it everywhere because we use the measurement that you have. You send the data to Evronet.
Yes, and then
they will ask for some constant, like air mass range, to perform the Langley, and then they produce the data.
And then if you have a day where it's stable enough, you can use it as a Langley. Okay. I get it. Thank you.
Any other question? Or somebody online? Please put your microphone on if you have questions. No? Then thank you again, Alberto. And we can move on to Antonis Gikas from here, actually.
So I can start. Good afternoon, everybody. First of all, I would like to thank you, Stelios, and all the people involved in the HARMONIA COST for the invitation to participate in this interesting workshop. My name is Antonis Gikas. I'm an assistant researcher here at the Academy of Athens. And the topic of my talk is related with the dust climatology from spaceborne remote sensing observations. here, thank you. Here is how my talk is structured. I will start with a short introduction, then I will move to the description of the MIDAS dataset, which has been developed and which has been used in order to perform an analysis for the global and regional dust climatologies. An analysis also has been performed for the global and regional dust trends. Other researchers have also used this dataset. I will show you some examples, and I will conclude with the MIDAS upgrade and some upcoming activities. No. Okay, it doesn't work. So I will use this. So here is an overview of the role of dust within the Earth atmosphere system. This is a leaflet from the InDust, and you can see that we have the dust emission from the desert, arid areas, under the impact of strong winds. The dust is uplifted in the atmosphere and interacts either directly with the incoming and the outgoing solar radiation, but can perturb the Earth radiation budget indirectly by modifying the cloud properties. Dust is also can affect infrastructures, several anthropogenic activities, is transported over urban areas, it can affect the air quality and can cause health effects. And upon its deposition in solar panels, has impact on the solar energy production. Upon its deposition on the ocean, has impact on the fertilization of the seawaters, and also when deposits over snow and ice-covered areas can modify the albedo there and can accelerate the melting of the snow and the ice. From a global perspective, the main global dust pattern, besides with the well-known dust belt stretching from the western parts of the Sahara to the Eastern Asia, as it can be shown here in Sao Tal, based on meteorological observations. What you see here is the global dust weather frequency, but dust is not only limited near the sources, it's advected at various distances and at various directions based on the prevailing atmospheric.
Join the action, join the newsletter. Follow us on social media for news and announcement.